Dear all, thank you to attend my presentation. My today talk deals with go faster for process control using ellipsometry. First, I will introduce you the LTM. The LTM is a joint research academic lab with CNRS and University Grenoble Alpes, and we focus on upstream technological research on industrial tools. We have two teams. Prospect team studies plasma etching and material integration for microelectronic. Minatec team focus on micro and nanotechnology for health and microelectronic, especially concerning lithography and metrology. Our targeted applications are low power component, photonics, memories, sensor, biosensor, and so on. So LTM is involved in the project MADEin4. We intend to get more out of the metrology steps. To do this, we increase the knowledge and the robustness of the classical metrology steps, and we also looked at how to go faster when you are trying to detect process deviation. To do this, we use the metrology tool that is unique. It is a cluster of characterization that allow you to load 300mm wafers from different process modules in order to assess and validate new hybrid concepts for inline metrology. This work is done in close collaboration with STCROL to ensure the inline compatibility of the solutions. To look further on impact cluster characterization, we have three chambers: an XPS chamber that is dedicated to surface analysis, an ellipsometry and polarimetry chamber for optical characterization, and a Raman photolume in order to notably detect stress in samples. During the project, we developed actions in order to increase knowledge and robustness by doing hybridation between XPS measurements and several optical techniques for ultra-thin film metrology. The robustness was improved by doing hybridation with CDSAX measurements in partnership with LETI. We also developed a new way to use ellipsometry for fast critical error detections on large surface of 3D patterns. So metrology intends to provide metrics for process development and control. And if the metric you measure belongs to a given confident interval, you continue the process, else you stop the process. Mainly, metrology tools are non-destructive, except punctually for R&D purpose. And metrology dies are now very, very small and located in cutting paths of the wafer in order to waste no area of the wafer. Metrology tools are highly sensitive, exhibit high accuracy, reproducibility on the measured metric. You have metrology tools dedicated to topography, others to patterns dimension, and finally, optical metrology that will allow you to obtain metrics, but that are dependent on the model you are using. So, how to get more using ellipsometry for process deviation detection? Ellipsometry consists in measuring the polarization change of the light after reflection. So you will have a light source, a polarization generator, a polarization analyzer, and a detector. At LTM, we are using a phase-modulated ellipsometer that exhibits quite low throughput in a spectroscopic mode, let's say 2 minutes, but a very high throughput at one wavelength, below 50 milliseconds. In semiconductor facilities, other kind of ellipsometer are used that exhibit high throughput during the spectroscopic scan. The order is some seconds, so it is highly efficient for inline metrology. So as I say, ellipsometry do not measure directly the matrix. You will need a model in order to obtain what you want to measure. If you are studying planar layers, you will do what we call classical ellipsometry and measure thicknesses, optical indices, and the number of the layer you have on the silicon wafer. Using the same technique, but on patterned grating, you will use a mathematical code that is scatterometry that will allow you to reconstruct the pattern shape. But it depends on the model, of course, and it is time-consuming. It necessitates deep development to be operational and long computation time to solve a new problem. So how to detect error or deviation more quickly? You can bypass the model or speed up the algorithm. To bypass the model, you can use artificial intelligence algorithm. The ellipsometer we use at LTM is the optical chamber of impact, and this is a unique ellipsometer that works in a very broadband range from 150 nanometers to 2 microns by ellipsometry, and you can extend the range up to 11 microns using the polarimeter. We have 300 mm wafer mapping capability, and the stage and the sample is maintained under vacuum in order to prevent any surface contamination or oxidation. Classically, you use an ellipsometer in the step and repeat mode in order to cartography a wafer. So you have a limited number of measure spots, and in our case, the smallest spot size is 300 per 300 microns. What is original in this study is that we developed a new acquisition scenario that we call the Raster Mode, and with a collaboration with the supplier with Horiba, we upgraded the hardware of the tool in order to measure in real time the variation of the raw signal while the stage is moving at a known speed. And once you have finished, you can reconstruct an image by adjusting the recorded signature with the position in time. We still have a low throughput, but a high resolution. For instance, if we are scanning a 200 per 200 mm scan field, we will have more than 400,000 measurements. In a raster mode, it lasts 6 hours. If you want to do it in the step and repeat mode, it is estimated to 50 days, so not possible to do. We believe also we can speed up a little bit raster mode scanning thanks to the detector, but we are still limited by the stage displacement velocity. So as I say, we collect data, and after we reconstruct the image we scan, we developed automatic algorithms that correct aberration in the image, and we record two images on two channels, ES and EC, as you see here. Once we developed this mode of imaging using ellipsometry, we test it on RED wafer that ST supplied to us. This RED wafer exhibits a control dose variation, and we wanted to check we were sensitive to it using the ellipsometer imaging system. And as you see on the picture to the right, we are sensitive to this variation. Those variations are not detected using a conventional defectivity tool. If you look at a local scale, you can also see that we have a resolution that is sufficient when compared to defectivity images. However, we may wonder if ellipsometry imaging system has a resolution sufficiently high to detect defects. So to do this, we benchmark the system on two use cases. One concerns stress on product wafer. It means a wafer you cannot model exactly. And on striation that were detected on two imaging systems during the coating of the imaging system with color resist. What you can observe is that ellipsometry is sensitive to detect the stress on product wafer. This is the upper part of the images you have on the slide. And we are also able to detect a striation locally in imaging dyes. And we compare always with a defectivity tool, a metrology tool STU, that is an interferometer, that is more dedicated to stress detection and topography variation detection. We were also able, as I said, to image 200 per 200 millimeter square field. We are able only to make square field using our raster mode. And what you see is that we are capable of imaging properly quite the whole surface of the wafer, and we are also still sensitive to striation locally. So, concerning this system, we can say we have a very sensitive metrology technique that is sensitive to slight variation of topography and to slight variation of the optical properties. So, to us, ellipsometry imaging system can supply to metrology and defectivity departments sensitive images to monitor process deviation. But we have still nowadays a low throughput due to the raster scanning mode, and we are looking for future collaboration with a metrology supplier for the development of a new system. And then we will transfer the know-how. So now let's move to scatterometry, how to go faster. Scatterometry is divided in two categories, I would say. You can obtain signature using classical ellipsometry that will measure two elements of the Muller matrix, or you can use a Muller ellipsometer that will measure almost all the parameters of the Muller matrix. Often, you can use only two elements to reconstruct the pattern shape. What is long in scatterometry is to model the scatterometry signature from a given geometry and then to compare it with experimental data. We increased a lot throughput of the simulation by decreasing it at minima by a factor 2.4 using different strategy. This is only for the simulation step. So it also increased a lot the pattern shape reconstruction because you have to do multiple iteration in order to minimize the difference between the simulation and the experimental signature. So it can take, it can last extremely long if the initial simulation is long. We we tested our code on optical diffusive patterns that are 3D patterns rather complicated to model. ST Kroll sent to us Muller matrix measurements with characterization using SEM with a cross dimension of the top and the bottom of the hole. And we launched an optimization in order to test if the scatterometry CD will correspond to the SEM CD. As you see on the curve to the left part, bottom left part, we are able to do it. We have a rather good confidence interval, and what you have also to understand is that scatterometry allows us to obtain the CD, of course, but also the thickness of the layer that define the optical diffusive pattern. The optimization of the algorithm allows us to model and to optimize the difference of the experimental signature with a simulated one in some minutes. Before it will have taken almost days. So what we can say is that the scatterometry code we develop is able to handle Muller scatterometer signature. It is a model dedicated to 3D patterns, and we were able to drastically reduce the time of computation. So it addressed the booster 2 of MADEin4 to go faster. So now, how to go faster than faster? To do this, we used artificial intelligence algorithm. What you have to know is that artificial intelligence algorithms are very efficient once properly trained. We use three categories of machine and deep learning codes. We used neural network, convolutional neural network, and regional convolutional neural network. The first use case we addressed using artificial intelligence was on the automatic detection of striation on imaging dyes ST encountered in the past. To do this, we trained an artificial intelligence algorithm, but using synthetic images, 200 to be precise. Once trained, we applied the algorithm in order to detect the striation on the ellipsometry images we obtained previously. And what we demonstrated is that we were able to detect with a success rate of 96% the striation in the image. The second use case we use to train and to test the machine and deep learning case concerns the dimension of the optical diffusive patterns. To do this, we train a neural network using experimental Muller matrix, CD same measurements on the sample. We use it to train the neural network, and after we predict, in fact, the measure CD. And what you can see on the curve, the predicted CD by the neural network is identical to the SEM CD measured. The prediction is excellent, but maybe too much, so we are thinking we are overfitting. In order to avoid any overfitting, we change a little bit the strategy for the training of the neural network. This time we use a convolutional neural network, and we train it, but only using synthetic data. In fact, by speeding up the simulation code, we were able to generate a massive training set. It lasts for 4 minutes, and this massive training set has 45,000 Muller elements. So we use this massive training set to train the CNN, and after we use it to predict the CD, but on experimental data. And as you see, we have a rather good prediction of the CNN CD compared to the SEM CD. It lasts only 2 and 3 seconds once trained. If you compare it to what we will obtain using a rigorous optimization that will last 2 hours in this case, we have almost the same accuracy. But of course, we are much more faster. To give you an overview of the use of artificial intelligence at LTM, we are using those codes for metrology purpose in order to reduce drastically the computation time. We also use machine and deep learning when we need to hybridate measurements of different metrology tools, because these tools are able to handle data of different type. And we also use it to detect objects in an image. For instance, to the left part of the slide, you have an automatic detection of defects in a wafer, green being good, red being not so good. And we also use it to detect, for instance, bacteria colonies for health application. To conclude my presentation, we can say that the imaging ellipsometer system we developed is capable of detecting defects because it has a sufficient resolution. We also demonstrated that we were able to decrease drastically the computation time of the scatterometric codes, and now we are able to predict the presence of defects on dies or wafers using machine learning and deep learning, or we are also able to predict metrics for complex 3D structures using machine and deep learning. So concerning the imaging ellipsometer tool, it is now a TRL 3.4 that is achieved, and we are looking for new partnership with metrology suppliers and microelectronic industry to move to TRL 5.6. Thank you for your attention.
So, good morning. Let me introduce myself. My name is Giulio Vivo. I am a senior researcher in Centro Ricerche Fiat, and together with my colleague Federico Magnea, we are working on the MADEin4 project with a contribution providing the perspective and the focused competencies of the automotive industry for this large Excel initiative, which is addressing as you already know, the advanced semiconductor metrology. And in particular, we are working in the task 5.2.3, which is dealing with digital twin methodologies and collaborative application for body and assembly shop floor modeling, simulation, and validation. And we support on this activity the task leader, which is FCA Italy, and we work in collaboration with Politecnico of Turin, with Comau, and with Brillantenor. And overall, CRF operate on the design and development of a digital twin, and on the establishment of a validation framework to identify and analyze energy efficiency or maintenance interventions. And for instance, the digital twin model, once it is completed, will allow to identify and to test the best solutions to improve the energy performance of the buildings in its obsolete parts, and consequently to propose focused interventions to reduce the energy consumption or to improve the indoor air quality for a better working condition of the involved workforce. So, while introducing the concept of a digital twin for an industrial building, everybody is definitely familiar with the physical counterpart of the twin, since there is nothing more solid and tangible than an industrial building. And less obvious is the digital counterpart, that in our case is targeting to the energetic aspects. And for this purpose, we adopt the virtual model, which is available in the building information modeling methodology. And considering the structural and stratigraphic features of an industrial building, it becomes available a relevant amount of data and information provided by a number of sensors of different types that are positioned in specific places of the different areas and locations of the building. And the digital counterpart of the twin is a virtual building that is kept running and consistently aligned with the physical counterpart thanks to this data flow, which is transferred in real time to the virtual building. And the purpose of the building information modeling methodology and the related data analytics in the digital twin is to carry out the correct processing and extrapolation of all this data to obtain a functional and validated representation in real time of the energetic systems and the components of the building. Clearly, this digital twin is a virtual model, so it is very important to select and to include in the analytics all of the relevant information needed to capture and to represent consistently the expected output parameters and the outcomes under investigation. At the same time, it is equally important to filter out all of the irrelevant information and data. And this is to avoid the drift, which is the defocusing and the insignificant detailing of the virtual model, and of course to avoid the waste of resources to process data that are not strictly needed for the complete modeling of the features implemented in the digital twin. And among the needed information, of course, the virtual model of the building should contain the geometric and structural information together with the energy related data and characteristics such as the systems, the type of insulation, the opaque envelope, the glazed structures, and the energy inputs, climatic conditions, and so on. So in this context, we introduced the acronyms of BEM, which is Building Energy Management, and PEM, which is Process Energy Management, to identify the energy models of the building, applying this digital twinning approach to the domain of the heat engineering and energy performance. And the purpose, as reported in this slide, is to enable the implementation of energy management use cases relying on the relevant features of the industrial buildings, including the design, the implementation, the control and the maintenance of the energy assets. Okay, in this slide we introduce the concepts of BEM and PM. And regarding the description of the methodologies, the BEM is used to estimate the energy consumption for the thermal conditioning of the air in the building using a digital model that should be complete as much as possible, integrating both the building structural features and the process loads. And the process loads, indeed, are estimated with the PEM, which is a dedicated mathematical model for evaluating the consumption of the industrial processes running in the building. Altogether, the BEM and the PEM methodologies are used to create the digital twin that we already introduced. And once it is validated, this digital twin allows to evaluate the effectiveness of the energy efficiency solutions. Just a few words on the state of the art. And currently it is important to say that there is a little objective knowledge of the thermal behavior within industrial environments, and also a widespread and common methodology is not applied for the energy analysis of the building relating to the plants, and there is a lack of tools to objectivize the effectiveness of building intervention solutions in the industrial domain. As a solution, the BEM plus PM methodology is introduced to objectively evaluate the energy and economic savings of the proposed building improvement. And the BEM plus PM represents a predictive digital mathematical model that allows to evaluate the maintenance interventions to ensure the indoor quality of the working environment. In this slide, we show the workflow of the BEM plus PM methodology. And the phases 1 and 2 and 3, they regard the development, the implementation and the tuning in a iterative loop of the digital twin. And in particular, the phase 1 is the design and implementation of the partial BEM three-dimensional model of the building, mostly focusing on its structural and stratigraphic features, including architecture and the heating, ventilation, and air conditioning systems. The phase 2 is the study of the process loads using the specific PEM methodology. And the phase 3 is the integration of the PEM within the BEM methodology. Phases 4 and 5, they regard the process outcomes, and specifically the phase 4 is the validation of the complete BM plus PM model by comparing the estimated consumption for heating the building with the real ones of the plant. And the phase 5 is the analysis and evaluation of possible restructuring and maintenance intervention to achieve energy and economic savings. In the next slide, we mostly concentrate on phases 1 and 2, which is the summary of the activities carried out so far. Then we will provide an overview of the intended oncoming and future activities planned for the next year. In this slide, we briefly summarize the activities carried out in the first phase regarding the model area and the input data. And some deepening and detailing of the related achievements has been discussed already during the last on SEMI ISS symposium on last April 2021. On the model area, we can say that the Mirafiori paint shop is a very large industrial area of more than 98,000 square meters with significant process thermal loads. And this settlement of Mirafiori is characterized by buildings of different types, such as office buildings, the assembly and body workshops, and even some buildings for commercial facilities and exhibitions. On the left part of the slide, there is the list of the input data, which is the information necessary for the design and implementation of the partial BEM model organized by topics. And we used commercial platforms to implement the digital twin. And for instance, the architectural and stratigraphic modeling is carried out in Autodesk Revit. And this 3D model and structural information is exported as a GB XML format file. And this file and information is afterward ingested in the design builder environment, where it is associated and fused with the climatic and scheduling information. In the same data processing environment of design builder, it is carried out the modeling of the heating, ventilation, and air conditioning systems and components. Note that at this stage it is already possible to make some first evaluation and running of the partial BM model, and as you can see, if we attempt to do this testing, you see the result contain significant drifts and discrepancies that are highlighted in red into this part of the slide, and this is pointing out the fact that in the paint shop area, the contributions of the process loads, which is not included into this partial model, is not negligible as we expected, and this demonstrates that the phase 2 of the modeling, which is the integration of the PEM in the model, is definitely needed. There is to say that other workshops, for instance, and other buildings, for instance, the General Assembly or even the office buildings, into these different locations, the weight of the process loads is not so relevant. So even a partial BM model can be successfully, let's say, deployed into these different use cases. In this slide, we show the calculation and the workflow of the process loads described by the process energy management methodology for its subsequent integration in the already prepared hosting environment, which is the one of the overall building energy management model. And as we anticipated, you see the location of the paint shop area, which is highlighted with red borders here into the map, in the context of the overall Mirafiori settlement, and the activities marked with ticks, which is the phase 1, the complete phase 1 and phase 2, are already completed so far at this time. And in the next slides, we will make some deepenings regarding the phase 2, and in particular on the process thermal loads identification, characterization, and on their collection and data processing. The output is the numerical representation of the overall thermal loads, which is the heating that the running industrial processes transfer to the building. And the working process here is planned for the next months. Is the inclusion, regards the inclusion of these relevant process loads within the partial building energy management model to complete the digital twin with all of its relevant components. Here we spend some words about the identification and characterization of the thermal loads inside the model area. And the painting processes that are relevant in terms of thermal contributions are highlighted in green. There are these small boxes in the map, and it is important to describe these processes in terms of their locations and the thermal behavior to obtain the splitting with the highest possible granularity of the thermal loads in the individual thermal zones. And the processes composing the painting blockchain are individually studied and furtherly decomposed into their relative blockchains, in order that almost all of their relevant thermal features are at the end properly identified, characterized, and included in the model. In this part of the picture here, we show some pictures, just some screenshots taken from the Microsoft Excel sheet, which is used to implement the process energy management model. And once the relevant blocks that are relevant in terms of thermal contributions are identified, the characterization of their relative contribution to the thermal load of the whole process is carried out by using simply the analytical formulas of the thermal balance that are embedded in the spreadsheets. And on this aspect, yes, I forgot to mention since the beginning that the digital twin that we are implementing is based on a numerical model which is completely deterministic, meaning that no artificial intelligence or machine learning solutions are adopted for its implementation. Here we have an overview of the various thermal contributions of the processes that are more significantly affecting the heating consumption of the building by pointing out the type of output which is expected based on the studies and the analytical characterization carried out for each one of these individual thermal contributors. We have identified 5 different categories of thermal contribution as we see in the slide, and we will further discuss this summary on the next slide. And the output from all contributions will be collected and integrated in the design builder, which, as we have seen, which is the environment where the energetic simulation of the overall building is carried out. Here we focus on the 2 contributors that we identified to the hydraulic balance. And the hydraulic flow, independent from the utility processes, is evaluated by means of a Microsoft Excel spreadsheet to calculate the airflow rate of the buildings in terms of external airflow infiltrations. And infiltrations are caused by the exchange between the air injected and extracted in the building due to the depression and overpressure zones that are created by the processes and by the heating, ventilation and air conditioning systems. And when the processes are running, some grouping of overpressure and depression thermal zones are obtained, are created. And in the picture, the macro areas of overpressure are shown in blue color, okay? And the depression are shown in red. And clearly higher is the intensity of the depression and greater is the infiltration of cold air that enter in the building from the outside. And as a result of the analysis for these first contributions, two air exchange values have been calculated for each thermal zone. And on is regarding the value when the processes are active, and off with the process inactive, not active. And the thermal contribution produced by the process airflow is evaluated by means of a second Microsoft Excel spreadsheet to calculate the thermal contributions on the building related solely and exclusively to the airflow, hot air coming from the openings of cabins, ovens and tanks. As output, the monthly contribution for each thermal zone is calculated according to the overpressure hot air flows and the temperature differences between the building and the process area. Okay, here we deal with the thermal contributions related to the tanks and the ovens. And regarding the thermal heating transferred from the tanks to the building, this is estimated by means of the process energy management methodologies. As we have seen, the implementation of the PM methodology is carried out by means of Microsoft Excel mathematical model, which is using the analytical heat balance formulas to define the convective, conductive, and radiative heat exchanges of the specific processes. And the calculation includes various input data and the characterization parameters to describe the features and the thermal behaviors of the tanks. For instance, the size, the dimensions, the process temperatures, the water flow rates, and so on. And as output, we have the average monthly thermal power, which is the heating transferred by the tanks to the building. As for the thermal contributions related to the ovens, and the procedure is exactly the same as the one carried out for the tanks. And clearly, in this second case, the calculations are based on input data, parameters, and mathematical formulas that are specific and characterizing the ovens instead of the tanks. And finally, we have the thermal contribution relating to the painting cabins that are the boot, the so-called boots. And again, we have a Microsoft Excel calculation on for estimating the heat contribution transferred from the boots to the building through the interfaces and the dispersing surfaces of the cabins. And then we have the identification of the areas of the dispersing surfaces of the boots for each thermal zone. And these are typically the ceiling and the walls of the boots, clearly. Then we have the calculation of the thermal transmittance of these dispersing surfaces. As a result, again, we have the monthly calculation of the heat, which is released to the thermal zone by the painting cabins, according to the dispersing surfaces, the transmittance and temperature differences between the boots and the surrounding air in the building. Here you can see the planned steps to complete and to conclude our work. In the last 6 months, we developed and completed the second phase of the planned activities, and we have good expectations on the possibility to complete the other 2 steps within the time frame of the MADEin4 project. That's all from my side. Thanks a lot for your attendance, and ciao.
Hello, welcome to the presentation of Robot Social Behavior Development for Automotive Manufacturing. In this presentation, me, Alfio Minissale, I am the European Project Manager of Comau, and Meirav Adad-Segev, that is the CEO of Brillianator, will show you the developments within the MADEin4 project about a new platform for social collaborative robotics. The presentation is divided in 2 parts. Here you can see the draft agenda, the agenda of the presentation. So in the first part, Comau will present the robots and automotive manufacturing overview with the challenge in the automotive sector, the use cases adopted, and the architecture of the platform. In the second part, Brillianator will show the collaborative social AI overview with the advantage of the solution, the way of working of the platform, and the result obtained so far between Brillianator and Comau. Okay, this is the first part, so just a brief introduction about Comau. Comau is a world leader in the robotics automated solution. Is a large enterprise located in the headquarters is located in Italy, in the north of Italy, in Turin, and the employees are more or less 8,500, so it's a big industry in company, and the funding is in the 70s, so we have a very good history and a good knowledge about robotics. We are present in 14 countries with 8 manufacturing plants, but we have also 7 innovation centers and 5 digital labs around the world. In the last year, one of the main challenges for us is the factory transformation following the revolution of Industry 4.0. Here in this slide, I try to recap which are the main steps to follow in order to, let's say, have this kind of transformation inside the factory. So starting from automation with different kind of devices that can be, for example, the anthropomorphous robot, but also mobile platform like AGV or drones, and also different kind of process that in the last years are coming to the market with very high frequency, like, for example, additive manufacturing. And then the second step is about digitalization of the data. So all the data that comes from the devices of the sensor and needs to be converted. And this here in this step, we of course we have some keywords like big data and the management of this big data, the Internet of Things, and so on. Another crucial point is the connectivity and the way to transfer this data from, for example, the edge to the cloud. And so here, very important is the use of some very robust protocol. And then in the end, of course, the analytics process that needs to be adopted in order to use this data for some specific purposes, like, for example, after-sales service, predictive maintenance, and supply chain. In the context of the MADEin4 project, we with Comau and Brillianator in this specific developments focused on the automotive sector. In particular, we're trying to analyze different challenges. For example, the first one is about assembling process. In this scenario, there are several robots that work together in order to achieve a specific assembling task. But of course, due of the high concentration of the robot inside the cell, inside the line, is very important to avoid any kind of collision in the area and any kind of disruptive interference between the different devices. So there is the need to avoid, of course, and to synchronize all the movement. And another crucial point is, for example, the way to cover and to have a backup in case of a malfunction of one of the robot, and try, of course, to cover this malfunction, trying to not stop the line and to have downtime that, of course, can have some economic feedback in the production. The second challenge is about autonomous mobile robot. Also here in the plants, in the production line, we can have different mobile robots that needs to share the same space and of course also avoid the collision. So through this platform is it possible to react to change, optimize performance, react of course to delay, and overcome also in this case malfunction, try to cover and to optimize the cycle time and the production output. Also together with the support of the end user, that is Stellantis FCA, now namely Stellantis, we consider some real case. For example, this is a picture that shows the production line in Cassino plant, where Alfa Romeo Giulia is produced. Here there is a very high concentration of robots in the same car frame can work up to 16 robots performing, for example, some assembling, but also some spot welding application. In this case, the production rate can be very high. In this case, is up to 30 cars per year, but in some other case, for example, for small car, can be also higher, up to 60 cars per year. So the needs of to have the production line ever running is quite important to avoid any kind of downtime. In fact, if of course one robot stops, all the line at the moment can stop producing, of course, lack of production and loss of money. This is the main architecture of the IoT platform. So in a glance, you can see the main components that compose the platform. In the main picture, you can see the specific also protocol and platform that are used for the overall architecture, and then we have also a focus on the Brillianetto social AI that can be described by Meirav in the second part of the presentation. In the next slide here, you can see some specific protocols and data sources that has been adopted for the platform. Specifically, we try to adopt some standard, of course, in order to have already a standardized solution that can be, of course, offered to the customer in a reliable way. For example, we adopted the OPSI-WAY protocol, that is a unified architecture that shows some very good interoperability feature, security, scalability, and complexity. Then we have, for example, the MQTT and the MQP. Also here, in this case, we have some feature like reliability and security. And the specific data sources, of course, are connected to the industrial control system, business application, and the sensor used in the components. Now I give the floor to Meirav that will show more in details the specific developments carried out in this specific scenario. And as said before, we will see more in details the advantage, the way of working of this platform, and the real results obtained in the demo situation scenario taken in the real factory. Thank you.
Thank you, Alfio. Hello, everybody. I am Meirav Segev, the CEO and the founder of Brillianetto. Brillianetto is a startup based in Israel, specializes in AI solutions for industrial robots. If we recall the challenges in deployment of multi-robot systems that were mentioned by Alfio, today robots lack the flexibility to respond to unexpected events. It is complex to pre-program them how to function with each other when they share the same space or in a case of malfunction and so on. But humans can easily share space and avoid collision. Humans communicate in a case of problems and switch tasks and so on, because humans have collaboration skills. They collaborate naturally. At Brilliant, we developed a unique collaborative social AI software platform based on modeling the part of the human brain in charge of collaboration. In our solution, using AI, we mimic human collaboration to enable robots to optimize problem solving, and this gives them the technical tools to work intuitively together. Our solution is a plugin that enables the robots to communicate and cooperate artificially with each other autonomously. Our quick and easily integrated plugin can be put into any existing system with minimal time, development, and cost. And it can be inserted to as many robots as you wish. Our product includes two major components. The first component, Brilliant Mind, is a software service connected to any robot. It includes advanced AI algorithms, via Brilliant Mind, collaborative AI capabilities are inserted in the robots. The second component, Brilliant Toolbox, is an SDK designed for the end customer. It provides ease and speed in inserting the Brilliant Mind to any robot. Using our product requires three major simple phases. First, we define information about robots and install the API on the side of the robot's controller. Second, we define and outline the goals that the robots are required to achieve at the toolbox editor. In the last phase, the operation phase, any robot with an API installed in it can contact the server and be guided and instructed by its mind in the Brilliant Mind service. As you can see in this block diagram, the Brilliant Mind, which is connected to the robot, gets real-time information about the environment from its robot's sensor. Based on this information, each mind decides and instructs its robot which actions to execute. The communication and the collective decisions processes are done at the Brilliant Mind level. This slide demonstrates how we define the metadata information about robots. As you can see, we enter all the information about the types of the robots into the system, including the basic executable actions that this robot can execute, like move to, close gripper, open gripper, grasp, and so on. We also enter the information it can receive from its sensors, named conditions. It includes, for example, the robot's position, distance from an object, and so on. Then, based on the metadata information, we define and outline the goals. Here's the example for the assembling process on the electronics field as mentioned by Alfio. Several of the robots are used for picking up the parts that arrive on the conveyor belts. They collaborate to assemble the parts and put the assembled parts on the third conveyor. The goals of the robots are to avoid conflict, assemble objects, and position themselves in the right position in order to do the work efficiently. Our toolbox editor is a drag and drop editor, and it is used to easily define rules of how the robots can achieve their goals. This little movie shows how one can easily define the rules. This slide illustrates how we define the rules for a conflict avoidance goal. In our specific example of an assembling process on an electronics field, the robots need to avoid collision as some of them share the same working space. In order to avoid collision, one robot should wait while the second robot moves on the shared area. As you can see, this rule is defined as a tree. The rule is for two robots. The first continues to move to the shared space, and the second waits. The end label at the left indicates to the robots that when they approach a situation where they need to avoid collision, then they have to communicate and agree between them who is going to wait and who is going to continue to move to the shared area. After we define the information about robots and install the API and also define and outline the goals, we can move to the last phase, the operation phase. In this phase, any robot with an API installed on it can contact the Brilliant Mind service and request a mind. The robot is connected to its own programmed mind in the Brilliant Mind service. The mind guides and instructs its robot how to behave while the communication and the collective decisions processes are down at the Brilliant Mind level. All stages of the decision-making processes are visually presented to the operator as collective decision tree diagram. We successfully integrated our product to commerce robots in both virtual and physical environment. In this little movie, you can see the results in a virtual environment. Brilliantor allows the robots to cooperate and communicate with each other autonomously and react to the changes in the dynamic environment. On the right side of the screen, you can see the decision tree of the robots. Here you can see how the robots cooperate to assemble parts. This little movie shows how they avoid conflicts. In this movie, you can see that the two robots work together with Brilliantor in a real physical environment. This movie shows that the robot on the left takes over the task of the robot on the right, as the right robot malfunctions. This is done autonomously, without pre-programming. Brilliantor's plugin allows them to communicate with each other and to say, hey, I have a problem, take over my task, and that means the line is not stopped. An additional example mentioned by Alpes comes from the logistic domain, where several mobile robots need to collect and deliver items based on priority. Our collaborative social AI allows them to communicate and to decide which robot is going to collect what, based on their location, in order to optimize their performance together. They also communicate and coordinate with the container robot. Here you can see how they successfully navigate unexpected events such as malfunctions. To summarize, we presented an innovative collaborative AI platform to enable robots to cooperate and communicate with each other autonomously. They act on unexpected events, make collective decisions, and act together to optimize performance. The platform includes an SDK that provides developers with an ease and speed in integration in their own system, featuring a user-friendly drag and drop editor and plug-in API that connects any robot to the Brilliant Mind. Brilliant is keeping up with the development of international AI standards, in which European countries and Israel have an active role in. To conclude, Brilliant's collaborative social AI platform was successfully integrated in commerce robots and allows deployment of multiple robots with user-friendly tools without pre-programming, saving development time, reducing downtime, and resulting in faster production speed. Our goal for the future is to find other real environments to prove the efficiency of the platform in different cases, such as industrial robotic arms, teams of mobile robots and robotic arms cooperation, or swarms of drones, and so on. Thank you.